Welcome. This is lecture 29. It's titled Morphisms, very generically. So what we want to understand in this lecture is, so now what do ring maps mean on spec, and how do we visualize them? What do they, using Morphisms, what do they translate into geometry? Okay, and the reason, so we will use this as a motivation to talk about finite and integral morphisms, and then proceed from there. Okay. So this is the setup that we have. R to S is a ring map, homomorphisms of rings. Okay. This gives a map from spec R, spec S to spec R, in which some prime ideal here goes to its contraction. Okay, so if we label this map phi, remember this is just a handy notation for phi inverse of Q. The notation, although the notation is that of an intersection, it is not implied that R is a subring of S. It is just a morphism. Okay, so this is what we have. And what exactly is this doing? That's what we would like to understand. Okay, so just one warning or note. We get a map from spec S to spec R. We right now is just a function. Okay, actually using in Zariski topology, it's even a continuous function. Okay. Spec S to spec R, but not from the max spec to max spec R. In general, okay. For example, think about localization. Okay. If you take the map R to R mod R localized at P, and P is not a maximal ideal, so the image of P inside here would be a maximal ideal, but its inverse image here is not a maximal ideal. Okay. So in general, we do not get a map from max spec to max spec R, but it so happens, and we do not need it. We do not need the result in our course, so we will not prove it, that if R and S are finite type algebras over a same field, and we have a map like this given by polynomials, then maximal ideals will contract to maximal ideals. However, that requires a proof, and it is a statement which is sort of it's very special to polynomial rings over fields, so or some similar rings. So we will not attempt at proving it, and we will not explicitly need it either. Okay. But let's try to understand this using some pictures nonetheless. Okay. So, so when we think about pictures, we will think of as K as algebraically closed. Okay. Although we will draw pictures here thinking that it's R. Okay, that is just for us to. Okay. Now we can ask, so what do maximal ideals of, let's say we take a simple enough equation, y minus x squared. Okay. So what is the max spec of this? Okay. Under Nullstellensatz, this is all the prime ideals, all the points in K2, okay, at which this function vanishes, or this ideal vanishes, and that just means such that B equals A squared. Okay, or we can think of it as a parabola. So again, when we draw a parabola, we're drawing it in R, but that's only for us to sort of keep a picture in mind. I mean, it's not this is over some algebraically closed field which can't be inside R. Okay, so this is okay. So we get a parabola. This is just this. That is just the axis. So the line, the curve is just the black one, and the blue thing is just the axis. You can think of it as x-axis and y-axis. Okay. So now let's look at a map of rings. The above ring kxy mod y minus x squared, and a ring map from kx, and x goes to x. Okay. So we can think of kx as some subring of this. So kx adjoined y, and then we say y is y minus x, kill y minus x squared. Okay. So this is just this, we said, corresponds to this parabola. Okay. And this corresponds to an axis like this. Okay. We can think of it as k itself, because maximal, so when we draw pictures, we are thinking about the maximal ideals, and the max spec of this is of the form x minus alpha. So the maximal ideal here is of the form x minus alpha, maximal ideal is of the form x minus alpha, and that corresponds to the point alpha inside K1. So we can think of this ring as corresponding to this line, the way we thought of this ring. Okay. Now, if you have a max, so in this case, it just so happens that if you have a maximal ideal here, when you take its inverse image, it is a maximal ideal. So now the map here is in this direction, okay? And we would like to understand what are the fibers of this map. I mean, what sort of a map is this? Okay. In this case, at least intuitively, one can think, if you have a point alpha here, its fiber would be the point alpha comma alpha squared, because it has to satisfy y minus x squared. So the first one would be alpha, the second one would be alpha squared. So one can sort of imagine that, and that is indeed the case. And so we should now try to formulate this idea of finding fibers from the ring, from the description of the ring map. Okay. And we'll come back to this picture. Okay. So recall that we have a ring map R to S. Okay. So now there is a surjective map to, if I is an R ideal, there is a surjective map to R mod I. Okay. And there is a surjective map from here to S mod the extended ideal. The picture, on the geometric side, the picture is we have spec S mapping to spec R. Okay. The surjective map, okay, so the spec of this ring is same as the primes containing, one-to-one correspondence with primes containing I. So we can think of this as a closed subset. Spec of S mod IS sits inside as a closed subset of spec S, and here is spec R mod I, and then we get a map like this. Okay, so a picture like this corresponds to a picture like this on the geometric side. Now we would like to understand the fibers of this map, okay, which is what the picture there was. This is a quotient of a polynomial ring in two variables, so we can think of this as S2 S mod I something. It is not IS, but okay, it is something. And here we can think of this as, so this we can just think of as R. There is no I. So I agree that this is not the same as this picture, but it is pictures like this that we would like to understand, essentially, and to figure out what are the fibers of this map. So suppose Q is a point here. Q is a point in spec I mod IS, from which we just say Q contains IS. So abuse of notation, here we are discussing a prime ideal of the quotient, but here I am looking at its pre-image and just calling it again Q. It's not very, there will be situations where one shouldn't do this, but this is not one of them. Okay? So Q, which now implies that Q contracted to R will contain I. Right? So this is indeed so we were given only this arrow. We did not have this arrow. We just had these two closed subsets. By drawing this arrow, I had implicitly asserted that image of this set inside here lands inside this closed set, which I had not proved. And now I proved it. That if Q is an ideal containing IS, its image will contain I. So in other words, a point here will map here. So till then, this arrow was just, I had not proved that there is such an arrow. Okay. So now, conversely, okay, if Q contracted to R contains I, then Q will contain IS. Okay. So that's the other direction, which again is not explicitly stated here. Suppose I take a closed subset here of spec R, which is spec R mod I. What is its inverse image? Well, all the primes in the inverse image, inverse image through this map will actually be primes here. Okay, so therefore, we get this diagram. I had not checked that this is a meaningful diagram when I wrote it. Now we have checked it. Okay. So now we would like to understand what is called fiber over a point in spec R. We don't need to worry. So this explanation with I itself was just to justify that this diagram with 4 arrows is correct. Now we would like to understand the fibers of this map, spec R to spec S. Okay, so fibers of spec S to spec R. Okay. So what are points here? A point here is a prime ideal, P inside spec R. That means P is a prime ideal of R. Okay. Now let Q be a prime ideal of S such that Q contracts to P. Okay, so Q contracts to P. Okay, so what can it say? So then Q therefore is a prime ideal of, Q will contain PS. Okay, in other words, Q is a prime ideal. Q gives a prime ideal of S mod PS. Okay. So that's one observation about such Q. Another observation is for all R that are inside R but not in P, for all R that are not in P, okay, Q cannot contain phi of R. Phi is a map from R2. Because if Q contains phi of R, then Q intersect R will contain this little r, but that's not inside P. Okay, so the Q cannot contain this. Okay. This is true for all R. Okay, so let's put these things together. Q contains PS and does not contain phi of R for all R but in the complement of P. Okay. When can this happen? we can think of S mod P. So first of all, Q has to correspond to a prime like this. Okay. And okay, so notice that there is a map. Okay. So S mod PS. So this is an S module. This is also an R module. So we can invert elements of this R mod P inside that. This is a multiplicatively closed set inside R. We think of this as an R module, and then we invert this set. Okay, so we get some. Okay, so this will also be a ring. These things can be checked. Okay, so what it says is that. So what it is saying is that Q has this behavior if and only if Q gives a prime ideal of this ring. Okay, again, when we say R mod P inverted, we mean their images inside S inverted. Okay, so that's how R acts on S. Okay, so so this is what this fiber over P looks like. Every prime Q with this property, this is what it looks like. So typically, when we say the fiber over P, ring theoretically, we just mean this ring. So this will be a ring. So we'll just mean this ring. Okay. One can also think of it as we can invert elements. So going modulo some sub-module and localizing here commute with each other. So we could just first take S, invert all these elements, then take PS and invert all these elements, and then go modulo this. So, okay, but this is the ring that we have. This is the ring that is would be considered ring theoretically as the fiber over the prime P. Okay, so we can think of it in slightly just one remark. R mod P. So okay, one can reverse the order of localizing and inverting and going modulo. Okay, so one can interchange the order of localizing and quotienting. Okay, and can also describe this as, okay, so we can describe this as follows. We take R localized at P, then this gives a map to R mod P localized at S, and then we kill P R P. This is the same thing as R mod P localized in the complement of this, and here we would just kill the extension of this ideal. Okay, so we take that map and then go modulo this, and then here we would just kill the extension of P into this ring. Okay, so this is also another way to think about it. Okay, and yeah, so this is how fibers are described. Fibers of a ring. I mean, given a ring homomorphism, what do the fibers of the corresponding map and spec look like? Okay. So just one more observation that we would like to make here. Here we are first. So what is the operation? So this is. So we have R to S, then we take R mod P to S mod PS, okay, and then we just invert all the non-zero elements here. This is a domain, okay, R mod P is a domain, okay, so then what we are, when we invert, so when we apply R minus P inverse to, so let's call this map phi bar. let's call this map phi bar to phi bar. Okay. What are we doing? We take R mod P. Okay. So image of R minus P inside R mod P is a set of non-zero elements. Okay. So here we invert non-zero elements of R mod P. This is a domain, so the set of non-zero elements is a multiplicatively closed set. And then we do the same thing here. Non-zero elements to this ring S mod PS. Okay, so this is a more concrete way of saying what is going on in that thing. And what is this? This is the fraction field of R mod P. R mod P is a domain, so this is just a fraction field, and this is the map that you would get. Okay. So in particular, if P is a maximal ideal, we don't need to do this invert elements of R, non-zero elements of R mod P. R mod P is already a field. Okay. So inverting the non-zero elements does not yield anything new. So this is an important point in this, which will be useful when we go back to analyzing that parabola. Okay. So now let's so then it would just, what we will just compute here is if P is a maximal ideal, we just have to compute R mod P and S mod PS. That is all that we need. Okay. So then we just compute R mod P and S mod PS. Okay. So now let's go back to the example. Okay. So the map is Kx to Kxy mod y minus x squared. What does it? So here is the parabola. Maybe this was not a very, okay, sorry, let me because I want to project to the x-axis, let me reorient the diagram. Okay. So here is this where I, this max spec of this is just one line, meaning it is just K1. Okay. Here is this parabola, y equals x squared. Okay. Let's take some point here, alpha. That corresponds to the maximal ideal x minus alpha here. Okay, so the order in which we are doing is, we start with a point here, then we got this maximal ideal, then we do this computation, R mod P and S mod PS. The reason we don't need to do this, this bit here. Okay, so now let's take this ring and extend this ideal there. So what is K? So not just extend, go modulo that, S mod PS. Okay. So this ideal modulo the extended ideal from x minus alpha. So K xy modulo y minus x squared. This is S modulo x minus alpha times this ring. The ideal generated by x minus alpha in this ring. Okay, and this is just easy to check that this is isomorphic to kxy mod x minus alpha y minus x squared. Just add this generator also in that list. That's all that we have to do. Okay, and again, this is not very difficult to check that this is the same thing as kxy mod x minus alpha and y minus alpha squared. Okay, so this is okay. So now, let's go back to this calculation here. So the maximal ideal that we have here, the fiber over this thing is corresponds to the maximal ideal, the ideal corresponds to x minus alpha, y minus alpha squared, okay, and that corresponds to the point here alpha squared. Okay. So that is how we this calculation we do. Okay, so yeah. Okay, so we start with an alpha. We consider this prime ideal here. Extend it and see what is the quotient ring that we get. So it is a quotient ring of kxy modulo this ideal. So inside K2 it is the point alpha comma alpha squared, and so this is. Okay. So now let's do the same thing for the y-axis, where the picture is slightly different. Okay, so there I will try just to keep the picture in our mind. I will try to do it. I will change the orientation of the diagram. So now let me write ky to kxy modulo y minus x squared, and the map is y goes to y, just the usual map, a natural map. Okay, so it is ky, then adjoin an x and set that its square is y. Okay, so this is still the same, the parabola. This is the y-axis. So let me just for a picture, let's draw, so that it corresponds to this picture. Let's draw it this way. Okay, so then let's continue. Let's ask this thing again. So we take a point alpha here. We take a point alpha there. Okay, alpha corresponds to the prime ideal x minus alpha, maximal ideal x minus alpha here. Then we look at its image there. So let's work that out. kxy mod y minus x squared. So we could do the modulo the ideal, etc. So all that just amounts to this is this. Okay. So this is same as, okay, so this is isomorphic to kxy modulo. So y minus y is alpha and x minus x square is this. Okay, so we can rewrite this as x square minus beta. Okay, and so this is not alpha. Okay, so this is not a maximal ideal. The reason is, so for now let's just assume that characteristic is not 2. Okay? We are working over complex numbers, let's say. Okay. Then this is not, this has a decomposition, y minus alpha x, not alpha, let okay, so let beta in K be such that beta square is alpha. Okay. So x squared is alpha, which says that x squared is beta squared, and it has two solutions. Let's say we are in complex numbers, so it has two solutions: x minus x plus beta and x minus beta. Even if you are in characteristic 2, it will have one solution of multiplicity 2. So the description of the ideal will be different. That is the only case. y minus alpha x plus beta. Okay. So this ideal decomposes like this, okay. And each of them are maximal ideals. So this is a maximal ideal, that's a maximal ideal. So spec of this consists of 2 points, one corresponding to this maximal ideal and one corresponding to this maximal ideal. So let's go back to this picture. So along this alpha, okay. So for this alpha, there will be 2 points, okay, which corresponds to the the x value takes the 2 square roots of the y value. Okay, so this will be, let's say, alpha, let's say this is alpha, comma, minus beta. So all of this picture is only approximate because we are drawing the picture in R, while all of this is happening in some algebraically closed field. Okay, so here would be the point alpha plus beta. Okay. So we have these 2 points which are in the fiber of this map. So the map here is, remember, is in this direction. Okay. These 2 points map to alpha. Okay. And here, if you take an alpha, it will appear from this picture as if you take an alpha here, its fiber is empty, but that's false, because this is only some real picture that we're trying to write to understand what the actual situation is. However, there is just one point that we should look. Okay. What if alpha is 0? So this assumes that there are 2 distinct things, alpha non-zero. So this is only if it's non-zero. Okay. If alpha is 0, okay, then we would just get kxy modulo y minus x squared and y, which is just kxy modulo y and x squared. Okay. So if you think of it as a point, it is only a single point, because this corresponds to one maximal ideal x comma y. But as a ring theoretic situation, we don't want to think of it as one point. We want to think of it as a point with some extra structure, and which is that there are some extra functions. Okay, so this, so we will not. So this is strict. I mean, that point there that you're thinking about is not exactly a variety. It has some extra functions, some extra structures on it, which we will not pursue it any further, but at least we should keep that in mind. Okay. The fiber over 0 here is a singleton point. Okay. It's a single point, but it has some extra structure. It's all, so I mean, these are 2 distinct points, so the structure on individual points is simple, but here that's not the case. So this is the example of what these maps mean. Okay. So in the next lecture, we will look at the same a similar picture. So this is just where, depending on where we are projecting, the nature of the map changes, and we will take that as a starting point to understand morphisms between 2 rings in some more greater detail.